Let's jump into local differential privacy. Local differential privacy is where, given a collection of individuals, each individual adds noise to their data before sending it to the statistical database itself. So everything that gets thrown into the database is already noised, and so the protection is happening at a local level. So now the question is, how much noise should we add? Well, this varies, as we'll see. Let's start by remembering what we learned about sensitivity in database queries. First off, we saw in previous lessons the basic sum query is not differentially private. In truth, differential privacy always requires a form of randomness or noise added to the query to protect from things like a differencing attack. To discuss this, we're going to discuss something called randomized response. Randomized response is this really amazing technique that is used in the social sciences when trying to learn about the high-level trends for some sort of taboo behavior. So if you imagine that you are perhaps a sociologist and you want to be able to study how many people in a city have committed a certain kind of crime. Perhaps you're going to study jaywalking. So you sat down with 1,000 people and you wanted to ask each individual one, hey, trust me, I'm not going to tell anyone on you, have you ever jaywalked, perhaps in the last week? Well, there's this trouble that people are going to be reluctant to divulge this kind of information because it's technically a crime in many locations. And so the sociologist is worried that the results are going to be skewed because some subset of the population is going to answer dishonestly. And so there's this amazing technique wherein a certain degree of randomness can be added to the process such that each individual is protected with what's called plausible deniability. And it works like this. It's pretty cool. So instead of directly asking each person the question, the first thing that a sociologist will do is present the question and then say, I need for you to flip a coin 2 times without me seeing it. And if the first coin flip is a heads, I want you to answer my yes or no question honestly. Did you jaywalk? But if the first coin flip is a tails, then I want you to answer this question according to the second coin flip. So the idea here is that half the time, individuals are going to be answering honestly. The other half of the time, they're going to answer randomly with a 50-50 chance of saying yes or no. And the interesting thing here is that if a person says, yes, I have jaywalked in the last week, that person has a certain degree of plausible deniability that they're only answering because of the coin flip. So they have this natural level of protection, this sort of localized differential privacy. They have this randomness applied to their specific data point that is local to them, and that's what, in theory, is able to give them the protection that gives them the freedom to answer honestly and to provide more accurate statistics at the end of the day. And perhaps the most extraordinary thing is that over the aggregate, over the entire population, the individual performing the study can then remove this random noise because, as you can imagine, this process is that it takes the true statistic and averages it with a 50-50 coin flip. So in this particular case, let's say that 70% of people actually jaywalk, like in the real world. Then we know that when we perform our survey, 60% of our results will answer yes. Let's take this slowly. So since 70% of people actually jaywalk, this means that roughly half our participants will say yes or no with a 50% probability, and the other will say yes or no with a 70% probability. Thus, when we average these two together, the results of our survey will be 60%. And this is incredible. This means that we can take the result of our noisy statistic and back into the true distribution, or the true result. We can say, since 60% of people reported that they jaywalk, then we know that the true answer is actually centered around 70%. And we can do all of this without actually knowing whether any individual person jaywalks. Pretty incredible. So now, one thing we have to acknowledge here is that the added privacy comes at the cost of accuracy. Even though that we will, on average, still get the right statistics, we are still averaging our initial result, sort of 60%, with random noise. And so if people happen to flip coins in a really unlikely way, we might accidentally think that 95% of people are jaywalking. It's only, quote, in expectation, aka when we have an infinite number of samples, an infinite number of participants, that this noise disappears and we get the exact true distribution. Thus, we have gained privacy, but we've lost some accuracy, especially if we're only sampling over a small number of people. This trend is true throughout the entire field of differential privacy, and research in differential privacy can thus be grouped into 2 main themes. The main goal of DP is to get the most accurate query results with the greatest amount of privacy, aka how can we minimize the amount of noise that we are adding while maximizing the amount of privacy. The second goal is sort of derivative of this, which looks at who trusts or doesn't trust each other in a real world situation. Because if you add noise to protect two people who do trust each other, that noise was wasted and your query was less accurate than necessary. But if you forget to add noise between two people who don't trust each other, meaning a database curator and an individual, then you put one of them more at risk. So we want to minimize the noise accuracy trade-off, and one of the strategies there is to create flexible differential privacy strategies, which sort of fit with how people actually do and don't trust each other in the real world. But enough on that. Let's implement local differential privacy for ourselves.